So good morning, my name is Rachel Tereska. I work for NTM Engineering near Harrisburg, Pennsylvania. Today I'll be presenting an innovative application of 2D hydraulic modeling that used a hybrid 1D, 2D model in HEC-RAS 5.0. The study was used to request a letter of map revision from FEMA Region 3. So I'll give a brief overview of the project background, the original FEMA study done in the area, and the 1D modeling limitations for this site. Then I'll discuss how the model was set up with both 1D and 2D components in HEC-RAS in order to calculate an updated floodplain map, and as well as floodway limits. And at the end, we'll take a look at some of those results. This study was performed for Mud Swamp Creek in Luzerne County, Pennsylvania. Mud Swamp Creek has a small drainage area, only about 1 square mile, with the upper part of the watershed being steep and predominantly forest and farmland. In the lower part of the watershed, Mud Swamp Creek is mildly sloped and transitions to a wide, flat floodplain. There's also a residential community in the lower part of the watershed, so most of this talk will be focused in this area down here. The community has been established for over 50 years and has no flooding history in their development, even during major statewide flood events like Hurricane Agnes in 1972 and more recently Tropical Storm Lee in 2011. The length of Mud Swamp Creek within the county is approximately 1.4 miles and was previously studied and mapped by FEMA. The original FEMA map for the community was published in 1973, but Mud Swamp Creek was not mapped at that time. In the 1970s, FEMA performed a HEC-2 study on Mud Swamp Creek and published a flood insurance rate map in 1980. That mapped Mud Swamp Creek as a detailed floodplain with a floodway. The county-wide update in 2012 for Luzerne County did not restudy Mud Swamp Creek. FEMA converted the base flood elevations for datum and also adjusted some floodplain limits based on LIDAR, which was then available at that time. So first, let's take a quick look at the FEMA map from 1980. And just to orient ourselves, Mud Swamp Creek is flowing from right to left across the screen. This flood insurance rate map indicates the 100-year floodplain is a zone A1 with base flood elevations, along with the 500-year floodplain as zone B. So we're looking at the dark gray for the 100-year floodplain, and the light gray, you can kind of see this protrusion in the southern part, that's the 500-year floodplain. So for this study, we're focused on this lower reach, so we'll zoom into this particular area. You can see the street network shows up on the old FEMA map, and again, we get a closer look at the floodplain, the amount of that area that was mapped as a regulatory area. So now we'll compare it to the FEMA map update from 2012. This is zoomed into the lower reach that we just looked at on Mud Swamp Creek. In general, the floodplain limits appear to be the same. Okay, so now we're looking at the blue line work. And now we have an aerial photograph in the background, and that gives us a perspective of the number of homes and businesses mapped within that 100-year floodplain. And you may also be able to see the hatching along Mud Swamp Creek itself, and those are the floodway limits within the floodplain. So we compared the FEMA 100-year floodplain limits to the LIDAR contours and also performed a site visit. The northern floodplain limit is pretty much delineated based on contours, but it became evident that the southern floodplain limit was not physically based. It appeared to be an arbitrary boundary. From FEMA section J to the downstream limit, so here's FEMA section J in red. From FEMA section J to the downstream limit, topography would not encapsulate the flows, and indicated that flood flows during high events would actually leave the system, leave Mud Swamp Creek, and head into the southern floodplain. Additionally, the township described a similar flooding pattern, where high flows leave that channel, flow through the farm fields, and sometimes pond in a couple of the local streets near where the development first begins. These events have not affected homes, and that floodwater ponds in the streets until it can be pumped back into the creek post the event. So using the FEMA model and looking at the HEC-2 geometry, we'll look at FEMA Section J on this slide. FEMA Section J geometry is in red, and that's superimposed on the LIDAR geometry, which is in green. So that southern floodplain is here on the far left. This is the leftover bank. And as you can see, LIDAR is showing us we're losing elevation. We're losing ground as we move away from the creek. But what do we notice about the HEC-2 section? There's a vertical wall in that leftover bank area. And that coincides with the limit that was originally mapped on the floodplain map for the southern floodplain. So if we put the FEMA BFE over top of these cross sections, you can see that the HEC-2 cross-section would have limited the floodplain, whereas the actual topography indicates that the floodplain would continue to the south. Okay, so we have some 1D limitations we need to address. First, during flood events, flood flows leave the creek and do not rejoin the system. It's essentially lost to that southern floodplain and does not continue in a downstream direction. Second, the topography of the southern floodplain is extremely flat and does not contain the flow. It has 2D flow paths as it maneuvers the street network. Third, flood elevations will not be constant between the channel and the floodplain. All of these conditions are difficult, if not impossible, to address with a 1D model. So a 2D model would be better suited to address these conditions. Given these limitations and given the fact that FEMA had previously mapped this area, we coordinated extensively with FEMA to ensure that a 1D, 2D hybrid approach would be appropriate and acceptable for us to prepare a map revision. So before diving into the hydraulics, we first recomputed hydrology for this small watershed. The drainage area at the county boundary was more accurately delineated as 1.13 square miles compared to FEMA's drainage area of about 1.4 square miles at some downstream location. We used HEC-HMS with the Snyder unit hydrograph method and PennDOT's IDF curves for precipitation to calculate the 10, 50, 100, and 500-year events. The updated flows were more than 50% lower than the published FEMA flows and were more reasonable for the watershed's size and characteristics. The HMS model was also beneficial because it gave us a hydrograph for the unsteady simulation that we would be running in HEC-RAS. Next, we use the FEMA HEC-2 model as a base for our 1D channel portion of our model. FEMA had over 30 cross sections on Mud Swamp Creek, which is fairly close spacing for a FEMA model. The upper part of the watershed was predominantly 1D. Upper part of the watershed was predominantly 1D, so we pretty much left that as is. And we focused most of our modeling efforts on the lower half, where we started getting into more of the 2D and the hybrid condition that I described earlier. So what we did in that lower reach is we took detailed channel survey as well as LIDAR information to replace FEMA's geometry for sections A through O. That encompassed the developed areas in the farm fields where flow began to leave the main channel. A lateral weir was coded along the leftover bank, so this green line indicated here. and that provided the interface between the 1D portion of the model and the 2D area. This was a critical component of our HEC-RAS model since the lateral weir calculated how much flow would remain in the system and how much flow would leave the system and head into the southern floodplain. For the Weir coefficient, we performed a sensitivity analysis in HEC-RAS, and we also compared it with another 2D model, TUFLOW, in SMS. So using those calibration tools and sensitivity, we determined that nearly half of the 100-year flow leaves the system and spreads into this southern floodplain area. This resulted in a 100-year flow of 270 CFS at the downstream most limit of our model. On the other side of the lateral weir, we connected a 2D floodplain using a 30-foot grid resolution in HEC-RAS 5.0. The 2D grid covers an area of about a third of a square mile and consists of most of this developed area in Luzerne County. HEC-RAS version 5.0 performs 2D routing with Saint-Venant and diffusion wave equations. So let's take a closer look at the modeling limits. We have the 1D cross-sections along the main channel. So the cross-sections are shown in red and the main channel is in dark blue. They are in the same location as the FEMA cross-sections. The lateral weir in 2D area begins where the topography changes and flow begins to leave the system. Any flow that passes over the lateral weir moves into that 2D area and remains in the southern floodplain. The 55% of the flow that stays within the main channel continues downstream along Mud Swamp Creek. Our upstream boundary condition was our hydrograph from HEC-HMS, and our downstream boundary condition in the 1D was a normal depth boundary condition. One other note is that we had to tie into the downstream county for our 100-year floodplain limits as well. So our next few slides are going to focus on the 2D area of the model. The red boundary outlines our 2D area. And we're also looking at the contours for existing ground elevations. And this is plotted showing using HEC-RAS mapper. The boundary conditions of our 2D area consisted of the lateral weir in green and also a normal depth in red on the southern and western edges of the grid. This is a plot of the 100-year water surface elevation within the 2D area. So anywhere where you're seeing shades of green is the 100-year event. We can see flooding of some streets and lower lying areas like detention ponds that are hydraulically connected and athletic fields. Another way to display those same results for the 100-year event is to use the average flow depth. This plot shows areas with less than 1 foot of flow depth in light blue and greater than 1 foot of flow depth in dark blue. This type of 2D output will be used later when updating the FEMA map with the appropriate flood insurance zones. We also coordinated with FEMA for guidance on the floodway modeling approach. While the 1D, 2D hybrid model was used to calculate our floodplain limits, the floodway model would only run the 1D portion of the model as steady state. Also, to be consistent with the flow reduction in our floodplain model, the floodway run used a flow change at the upstream end of the lateral weir to reduce the flow through the downstream reach of Mud Swamp Creek. This was necessary to ensure that our floodway run could meet the 1 foot surcharge requirement for floodways. The upstream floodway remained mostly unchanged, but the floodway widths in the downstream reach were significantly reduced. On average, floodway width was reduced from about 150 feet to about 25 feet, which basically contained the new floodway to the main channel itself. The 1D to 2D hybrid model resulted in a more accurate floodplain delineation along Mud Swamp Creek. As we'll see in the following slides, a Zone AE detailed floodplain was calculated with the edge of the Zone AE along the lateral weir. Zone X shaded maps the areas with 100-year flow depths less than 1 foot. Identifying areas of shallow flooding was especially important because Zone X shaded does not have mandatory flood insurance requirements. The 1D, 2D results also decreased the 100-year water surface elevation by a maximum of 2.5 feet when compared with the effective FEMA map. The 1D, 2D results were used to map the floodplain shown here. Along the channel in red is the new 100-year floodplain limit. In light blue is the revised 500-year floodplain limit. The red islands in the southern floodplain are isolated areas with average flow depths greater than 1 foot. So let's superimpose these results on the effective FEMA map. Recall at the beginning of the presentation, the blue hatched areas were the 100-year floodplain, with the diagonal hatching representing the floodway. The black hatching in the southern portion of the floodplain was the 500-year event. Compare that now to the revised 100-year floodplain shown in green. Okay, it's actually not visible for a portion of the channel because the floodway line is on top of it in purple. The 500-year floodplain limit is shown in orange. Okay, and those isolated areas of flow depths greater than 1 foot are those islands of green. So while some additional areas in the southern floodplain are being added to the 500-year floodplain, most of the development on either side of the channel is being removed from both the floodplain and the floodway. So to conclude, adding a 2D component to this hydraulic model enabled us to allow flow to leave the system using a lateral weir and reduce the flow in the downstream reach. It also accounted for the 2D floodplain characteristics and the calculation of an average flow depth in the floodplain. In the end, our results significantly narrowed the floodplain and floodway, and the updated floodplain limits will provide a much more accurate floodplain map to the township. And with that, I'd be happy to answer any questions. Yes?
So could you go back to the original FEMA flow rate with the original effective versus what you calculated in HMS? So you dropped there was a dramatic drop in discharge, and then from the lower discharge, then there was another drop in discharge based on the lateral weir?
Correct.
And in terms of calibration of previous rainfall or watermarks, was that some information you were able to obtain?
Yes, because there's so much development along the creek, there would have been flood history of previous flooding of those homes or yards or things like that. We had people that were previously located in the floodway that were never ever seeing flooding. And so that did validate the results that we were seeing. And it was much more updated methodology as well. The FEMA methods were decades ago.
Could you talk a little bit about some of the differences in that methodology that changed? Just a lot of...
Yeah, the FEMA flows were like a regional study, so, Northeast Pennsylvania or county-wide, and we don't have the calculations for what FEMA did, but there was nothing that we obtained that would substantiate them.
For the whole reach as opposed to at the different street locations.
But even more regionally, like more of a region to the state, rather than us just focusing on the physically based characteristics of this particular watershed and the flood history through this reach. Scott?
Was the reason for the 1D, 2D hybrid just so you could do the floodway in the main channel? Or I'm wondering why the whole project was just 2D.
Honestly, we didn't expect from day one that we would end up with a hybrid. We thought that we would be able to do a regular 1D update until we learned more about how flow was leaving the system. And since we knew we were destined for a map revision, we felt it was easier to keep the FEMA sections in the mix. The channel was still acting 1D, and we just had to account for what was happening in the southern floodplain. And so that was how the hybrid came to be. Yeah, but good question. Black shirt?
How did the TUFLOW compare with the 1D2D hybrid?
Good, and the other thing we used the TUFLOW for was to help us decide where to place the lateral weir, so not only the coefficient, but where flows started to diverge from the channel and where to best place it, because there really wasn't a distinct topographic feature to code in a lateral weir, and so it ended up being a judgment call. So obviously some differences in water surface elevation between the TUFLOW and the RAS, and it was used as more of a calibration tool. It wasn't as detailed. We didn't have bridge crossings coded into the TUFLOW like we did in HEC-RAS. So close, but not perfect, yeah. I think it would depend where you were looking in the reach, yeah.
So we're gonna table some questions, but at the end of this break is lunch, and grab Rachel and ask her some questions.
I don't need to eat, it's fine.
Take it out of the
Thank
lunch
you.
and take it. Thank you.